Hi, welcome to Toronto, Canada on this snowy day. I'm Duncan Brinsmead, I'm Principal Scientist with Alias. I'm going to be showing you a few tips and tricks on how to use Maya Fluids feature. Why don't we come on into the office here and we'll go upstairs and get Nihar. He's going to help us out a bit. You know, an important thing when you come here is make sure to grab one of these candies. They're really good. Okay, this is our lobby here as you come in. And we've got our Academy Award in a nice bulletproof box here. Okay, and we're going to show some rather detailed stuff on fluid expressions using particles and spray, kind of show you how to set up some oceans, create wakes and splashes, and also do a range of cloud effects. But we're going to concentrate on the dynamic interaction of particles and fluids. And so it's going to be quite technical. Oh, and look, here's our visualization center. This is brand new. It's a cool facility. We can bring in customers and show them all kinds of stuff here. We've got, you completely get surrounded by screens. And we can also try out new interactive experiences and stuff in here. Here, let's go and get Nihar. So this DVD has on it a number of technical examples on how to use fluids. It's not for beginners, really, so you should have some background before using it. And the examples themselves are not finished examples. They're more just illustrating principles you can use when you want to create fluid simulation. Doing things like crashing ocean wakes and things usually involve a huge range of techniques. So you probably will use these in combination to get your final desired effect. Oh, here's Nihar. Hey, Nihar. Hi, ready to do the Fluids DVD? Let's go get some coffee. I'm in desperate need of a little Java. Maybe even some espresso too would be good. Let me grab a cup here, get some coffee. I think Nihar doesn't like coffee, you know? I don't know what his problem is, but such is life. Okay, let's go start the DVD. Fluid Effects allows you to create a full ocean with a single button click under the Create Ocean command. Let's look at some of the options here. You can create a preview plane, which I'd recommend, and set its size. There's also an attach to camera option, which I'll explain a little bit further, a little later. For now, let's just create an ocean. And you see we have, there's a large circular plane that's created. And it concentrates, the design of this is just a NURBS plane, but it's been designed to concentrate most of the triangles in the center, so that as long as your view is close to the center, you get very good displacement on the polys. And then there's also additionally this preview plane object, which you can position around your ocean. You can translate it, and you can also even non-proportionally scale it to kind of preview the ocean in places. So you could create extra preview planes. You can set the resolution on it, and they'll play back and they'll show the ocean in movement, and it'll also show some of the attributes on the ocean like foam and color and stuff. Just to give you a better idea, sometimes you can attach this to where a boat is, maybe, so that you just see the ocean around where a boat is. And it's nice and fast to draw on the interface, which is nice. And then the actual rendering is done by the surface, which is computed as a displacement. The ocean shader itself does not directly have it has a built-in bump map on it, and it connects to a displacement node. And one of the things to keep in mind here is that the ocean shader it uses just uniform tessellation, or whatever the tessellation is on the surface. It does not use the adaptive or the on the shape under tessellation here. Sorry, under displacement map. there's feature-based displacement. Assigning an ocean shader will automatically turn that off because we don't want the tessellation to be adaptively refining when it's being computed. The other thing is that the displacement, the feature-based displacement is assuming that there's no bump phase, so it displaces the triangles, and then the normals are also displaced and reflect the displaced triangles. When feature-based is off, the displacement pass, it displaces the triangles, but it doesn't modify the normals. And then it's up to the bump phase to modify the normals. And this avoids certain linear interpolation artifacts you might see across your surface if your triangles aren't fine enough. So using the non-feature based is really what you have to use if you're going to use the ocean shader. And it doesn't have a separate bump on it. It has a built-in bump map, and it's got a built-in texture on the ocean shader. It's a little unusual for a shader. It's not only got say an out color and an out transparency, which most shaders have, but it's got an out displacement, which you can connect into things. Like in this case, it connects into the displacement of the surface. So let's look at some of the parameters here on the ocean shader. There's a scale parameter, which is generally you adjust to your scene size. So it's by default, the wave speed of 1 is trying to have about the right speed of motion where one of these units here is a meter. And in this case, then the wavelength would be defined in meters of waves, and then the actual speed of animation would come out correct. You can adjust the overall scale, and what that is saying is sort of what the general size of a meter is. So if you're saying that each of these units now, if I've said it like this, I'm saying each of these units represents 1.75 meters. And so we're essentially getting in closer to the ocean surface by doing this. And you can see the waves look bigger because we're proportionately closer. If we do this, if we make it like 10, then it's like we're way up in, quite a bit higher on the ocean. So also for speed, the default ocean settings aren't too complex in terms of the waves that you get. It has only 3 frequencies or 3 separate frequency groups. The more frequency groups you have, the slower it is to compute because it has to compute more waves on the ocean. And at this point, I also like to mention it. The ocean shader itself is not dynamic in that the waves aren't computed in reaction to forces, and you don't have to bake and simulate them. The waves are simply textural and procedurally generated, but they do match the nature of waves you get on the ocean, and you can get some nice wave peaking effects and things that are can be difficult to get with other means. So you've got these controls here that let you vary the behavior of the wave across the range of frequencies. So the range of frequencies is defined by the num frequencies, and then the spread of them is the wavelength min to max. So at the left of each of these graph widgets here, it represents the wavelength min, and the right represents the wavelength max. So let's say let's increase the number of frequencies a bit to 10. So now you'll get, if you want a turbulent ocean, and in general, more frequencies generally looks better. So we could make under wave height, let's make the wavelength max larger too, so we have like some, so we have some 10-meter waves. So now we have some very large waves mixed in with the small ones. We can, if we want to exaggerate the size of the large waves but not the small ones, here I can increase the wave height, and it's only increasing the height of the large waves, or the largest frequencies, but the small ones are still low. And you see, if I knock the small frequencies down to 0, it becomes very smooth. Or we could do the opposite. We could make the small frequencies high, and the large waves, we could knock down. in general, when you've got an ocean that's forming waves, sort of the history of how they're formed will determine partly the makeup of the different frequencies. Usually, I think, you know, your strongest frequencies are somewhat in the middle of the overall frequencies, and there's kind of peak areas where you'll get the strongest wave frequencies, and then it'll die out as they'll get to large waves. And on an open ocean, you might get, you know, 200-meter waves, but they're like very, very large and very shallow swells, so you wouldn't even see them, and you probably wouldn't even need to worry about trying to recreate them. So it's just a matter of finding, you know, if the wind comes up suddenly, right, it'll initially increase the height of the low frequency waves because the added wind turbulence makes them break up, and the small waves, right? The ones that are on the bottom. So actually the high frequency waves. The small waves will quickly die out. The large waves die out less quickly. So if you've had a storm that's distant and been brewing for a while, you have a lot of big waves that'll come, but there'll be no small waves on them because there's no current wind. So it's just kind of the remnants of big waves. So different conditions can create all different kinds of waves. There's a turbulence attribute, which is generally pretty useful. And I would, in general, for most conditions, just keep it all the way up. But in some cases, you might just want simple linear waves, in which case you can drop it down to 0. And notice that the moment this becomes 0, it gets a lot faster, because now it doesn't compute any turbulence. And when it's not, and then you can see the effect. If you just have one frequency, then we just have a simple wave happening, right? The wind direction determines the base direction of the wave, so we could kind of make it diagonal by changing the wind direction. And as we increase the number of frequencies, they're mostly going in roughly the same direction, but you can change the wave direction spread, and then the waves will tend to go in different directions as you increase the number of frequencies. And eventually, as you have enough frequencies, it becomes more turbulent. Note also, we might want to lower the wave height. The way the frequencies add up, in general, the more frequencies have, because they sum, you want to lower the wave heights so that you don't get huge, enormous waves. With wave peaking, one thing to keep in mind is it only works if you have wave turbulence. So if your turbulence, it only acts on the turbulent waves. So as we lower wave turbulence, you get more and more of just the linear waves mixed in with the turbulent wave groups, which are more expensive to compute. The wave peaking is only done on the turbulent wave groups. So generally, if you keep the turbulence all the way up, if you want to see wave peaking effects, it's the best. Now, notice if I have the wave peaking all the way down, we get smooth waves, and as you increase the wave peaking, there's this effect of the waves come together, and the smaller waves will get pulled along by the larger peaking waves, and you can specify wave peaking at the small wave level or the large waves. You might have some ocean conditions where you've got smooth waves in the low frequencies, but then the little waves are still peaking because a wind has just kind of come up and it's making the small waves peak. Okay, now in addition to that, we have some foam. And the foam, you just kind of have to play with it to get a general sense of it. But there's sort of a notion of foam emission. And the foam will look best if you have a lot of frequencies, because the more frequencies you have, the more noise frequencies you have in the noise texture that we're using for the foam. And I could just, if we want to see this a little better, I'll go to our preview plane and we'll up the resolution so we can better preview the look of the foam here. We could even type in values like 400 on the resolution, although then it starts to get a bit slow. There we go. Okay, so you can see that that was pretty slow. I'm not gonna bother looking. But one of the things you can see about the noise here is it has these sort of rings, and it's a kind of a assigned noise function that we use that kind of provides these kind of foamy ring-like looks. And again, the more frequencies you get, the more it's like a nice detailed fractal noise. Let's go back to 100 on the resolution and on the shader. Now there's a threshold which is sort of it's not just the total wave height, but it's the height of the individual subwaves. So it's the threshold is kind of like a curvature threshold at which it will a curvature and height threshold at which it'll produce the foam, and it's not dynamic foam. So this foam here is just simply a textural foam, but it kind of lasts into the trough of the wave. So what we do for the foam is evaluate the ocean at with a little bit of a lag in time based on the wave frequency. So the foam is actually, when a wave's trough is going down, it still thinks it's all the way up. So it tends to foam when the wave peaks, and then as the trough falls, then it starts to fade. So that's the general model. You can't kind of have the foam linger a long time as a wave's gone past. It only lingers one, half of a wavelength as the wave moves. So it's a nice trick, but it's there. If you need dynamic foam, there are other ways of doing that by hooking in a fluid node and using that to texture the foam values. There's also a general foam offset. This is usually what you would texture. It just adds on to the total foam value. And the threshold, as you can see, it's sort of the height threshold at which it emits foam. So if you want, let's say you want a really defined thick foam with a sharp edge, then you would create a lot of foam. Like you could even type in values like 3 or something, and then just lower the threshold, and then you'll get a very tight cutoff. Conversely, if you want it very loosely defined, you can make the foam emission a low value and then raise the threshold quite high, and you can get the foam just kind of gently formed over the entire ocean surface. Okay, now one of the things I'd mentioned was that you can have an ocean created that tracks the view. Now you see now as I move, the actual ocean surface, right, with all the triangles on it. As we get out here, we're going to lose our horizon now. And what we generally want the horizon to always kind of be off at infinity, basically. And also, we won't have very good resolution on the triangles as we do this. So as you move over the ocean, we'll get poorer and poorer and elongated triangles and stuff out here. It won't look good as we move over the surface. So there's a little trick you can use. Let's just create a new scene, and we'll create a completely new ocean. So now when we create ocean, I'll turn on attach to camera. Now, it might look a little weird. There's our preview plane. And as I now zoom in and out, notice how the preview plane seems to stay the same. And I'll track up and I'll track down. What's actually happening, we can see if we, let me just bring up a layout of, say, 4 panes. Now, in my perspective view here, as I move out, you can see that, here, we'll just zoom out here. There's our ocean plane. So as I go in and zoom in, you see the actual ocean plane here is getting smaller and smaller. Likewise, if I go up, the ocean plane gets larger, and as I go down towards the ocean surface, it gets smaller. So what it's trying to do, and also if I track, so as I move sideways, see the ocean tracks with me. So what it's doing is it's always keeping the triangles so that most of the triangles are right in front of the view or near the view. And so the horizon always stays there, and you can animate a camera moving over the ocean surface, and it will the camera can fly forever over the ocean, and you'll always have lots of triangles. You could even fly in amongst the waves, and there'll always be enough triangles to represent the peaking of the ocean as you move through it. So this sort of relies on the way the bump works with the ocean, because the bump is applied to the waves. So the actual triangles will sort of move over the ocean as you move the camera. But because the ocean's moving, you tend not to see this, and also because the shading itself is not affected by that. It's just the profile of the triangles is affected. You probably won't notice it unless you don't have a high enough tessellation, in which case you can just sort of increase the tessellation on the surface. So that kind of that way you can go way up in the air. You can see the ocean, through the clouds, and you can come right in amongst the waves and still have enough triangles.
So what I'm going to show in this file is a simple example of bump mapping. And if you look into the hypergraph or hypershade, you'll see that this is a familiar node network that you use for bump creating displacement shader or displacing the surface. But what you should notice over here is that uh, you don't see any actual displacement of the surface. So this displacement actually happens inside the render view, and it is evident if you see render editor's render view, and this is a rendering of the same view. But as you can see that there's this ring that is actually cutting into this geometry of cylinder, which you don't see over here. It's not actually happening in 3D space. It happens only when you render it out. And how that happens is, let's take a look at the hypershade. You can see that um, this bump map is applied to Blinn1. So if I look into the attribute editor, it's applied over here. And this is the bump or the ramp that is actually creating the displacement. Uh, you look at that, it's a simple circular ramp. What happens is kind of similar in the case of ocean shader. So this is exactly what happens in the ocean shader when you render it out uh, as a software render. The only difference being that when before you render it out, you're going to see the displacement via the height field, which is what we are going to see the next. So the next file that you see is you'll find the exact same shader network. It's the Blinn1 that has got the bump mapping. It's a circular ramp, exactly the same as it was before. But the difference over here, when you look at it, is that this displacement is being represented in 3D space in my perspective camera. So that actually tells me how it's going to look when I actually render it out. And this is all being done by a height field node. Although it's called height field, when you create it, it's being grouped under transform 1. So this is actually the height field node that does the representation. And in the attribute editor, you can see the familiar attributes of resolution, which is, if I increase that, you can see that it's a more accurate representation as you increase the number. Color is really not of much of significance. We just set the color as blue um, to represent the ocean, and then on top of that you sort of apply the foam that goes into it. Displacement is actually being driven by the bump map, and here's the height scale. So if I increase or decrease it, I can accentuate the actual bump that is being rendered. So if I render this out, it's going to be look exactly the same, kind of what I showed before. So let's take a look at how the height field actually gets this input. And if I go into the hypergraph, you'll see that the bump or the ramp that was being fed into the displacement has got its out alpha being fed into the displacement attribute of the height field, and this is how the height field knows where to actually show the displacement. And that's pretty much the same way how we use it for ocean. So over here I have a file open that shows how the color at point command works, and the file name is color at point example. What we have in this file is a simple setup where I move the sphere, and as you can see the sphere moves over the NURBS plane to which it is constrained. It picks up the color of the NURBS plane, and the color of the NURBS plane is being derived by a 4-color ramp. The way it is done is through an expression that uses color at point command. So I'm just going to briefly open up the expression editor, and the line that actually illustrates how color at point command works in this case is right here. Color at point in this case is taking inputs that tells it in terms of U and V space where to look for that color on the ramp. So the -U and -V values actually point it to a specific location on the ramp, which in this case is ramp 1. And the output over here for this case is RGB colors. So let's take a look at the hypershade, and if I look at the node network, it is pretty simple. The ramp is applied to the blin, and the ramp actually gives you the color of RGB values, which in this case I need to know where exactly I am. So the position of the U and V is decided by the position of the point on which in terms of U and V space where the sphere is sitting. So as you can see, this is the command that we'll be using quite often. This command was specifically designed for extracting color information and alpha information from the ocean shader, but as I'm illustrating over here, it also works on other shading networks.
I'd like to just add that, yeah, it works on the ocean shader in that it gets the XZ point in world space for the ocean shader. So the UV then essentially become an XZ coordinate that is derived from the ocean shader, which the ocean shader has a built-in texture projection projecting down the Z-axis. So the coordinates are in projecting down the y-axis, sorry, and so the coordinates are in X and Z. And then, but we also use this for any 2D textures. So you can get the color value from any of the non-projected 2D textures. And then there's one other exception, which is for ocean wakes, and you can get the value of a 3D ocean, or a 3D fluid texture. So fluid texture 3D, it will give you the coordinates in a similar fashion to the ocean, where you give the X and Z values.
So moving on to the next fluid command example is this file called fluid commands example, which contains a 3D fluid, and I'm going to show you how fluid voxel info and set fluid adder commands can be used for in conjunction with a 3D fluid. So what I have over here is a simple setup, and if I go into Solver's interactive playback, which has got a hotkey, so I'm just going to use that and press P, and then I will pick up the sphere, and as I move the sphere above the grid, which is the zero line of the y-axis, as soon as I move up, I start painting red fluid inside this fluid. And the way it happens is that I find out the voxels that are sitting inside the sphere, and these are the voxels in which I paint red color. The red color is being created by set fluid adder, and I actually set the density and the color. So let's take a look at the expression that creates this. And here's the expression where first I get the radius of the sphere, and I also get the location of the sphere in world space. At that point, I pipe these values into fluid voxel info. So here's the position of the sphere, and here's the radius of the sphere, and here's the name of the fluid, 3D fluid in which I want to do all these operations on. So going down to the next part, now that I have found out the voxels in which I want to paint, these are the voxels, or rather voxel centers. And then I take that information and pipe it into the set fluid adder command. And this is where I paint the density, and this is where I paint the color. This loop that you see over here is actually iterating through all the voxels. And if I find a match, then that's where I paint it. So this is the kind of setup that we'll be using for combining ocean shader, 3D fluid, and the old particle system that Maya uses. Alright, so in the next file that we have called Ocean Manual Example is something that shows you that you don't necessarily have to go through the usual fluid effects, ocean, create ocean menu to create your ocean, because the ocean that gets created through that menu is something that's a specially designed circular NURBS plane that's got a ocean shader assigned to it. There will be occasions when you want to create a little patch of ocean or water surface which is not exactly in the same shape as that circular NURBS patch. So let's say I want to create my own NURBS patch that has got ocean shader on it, and here's the example where it was created. So I'm just going to go through a quick workflow that shows you how it was done. So if I start with a new scene, I'm just going to create a new NURBS plane and just scale it up a little bit. And next thing I'm going to do is assign new material ocean shader. With the ocean shader assigned to it, you'll notice that it automatically turned off the displacement map, feature displacement. And also I could actually turn on the tessellation and change it to what I want. Now this thing doesn't have any preview plane, so to add the preview plane you can just go ocean shader, add a preview plane, increase its size, increase its resolution, and now if I go into the shaded mode, the NURBS plane is still being shaded. Maybe I don't want that. So going back to the drawing overrides, you'll see that if you select the NURBS plane 1, it has under its transform attributes enable overrides, and once I turn that on, I just click off the shading. So even if I go into the shaded mode, you can see that it's not really getting shaded, but at the same time, it does have the ocean shader applied to it.
So now we'd like to cover some ocean effects and how to handle waves. Just be careful though, because you do this too long, you can get seasick.
And along with the oceans, we will also cover a topic where we use mental ray for getting some nice reflective water.
Reflective water. I'd like to talk a bit about shading the ocean. The file Ocean Pond with Reflection helps show how to handle things like reflections of objects off of the ocean surface. You can make an ocean reflective by ray tracing it, although initially the parameters won't come out necessarily the way you'd hoped, and there are a few compounding factors. First, let me just talk about the setup I've got here. Just a simple sphere and an ocean. In this case, the ocean is, as in the workflow described before, where we've just assigned an ocean shader to a plane with displacement. So it's not a full ocean, although you could do this with a full ocean. And we have a wake. And in this case, I've modified it so that the wake in the preview plane here, it's kind of hard to see with this shading, but there's a little wake, and the wake has the ocean shader, but it's not showing any of the textural waves of the ocean. So the way you would do this is create an ocean and add a wake. And or you can create a wake for an ocean that's just assigned a shader, and it'll create a fluid, dynamic fluid wake on it. Then on the ocean shader, make the num frequencies 0. So once the num frequencies are 0, all you'll see is the wake effect. The wake is actually applied as a 3D. It's a 3D fluid texture applied to the wave height offset. And then in the 3D fluid texture, there's a flag is 2D, which is a hidden flag on the texture, and that has been set to true. So it's not actually a volumetric fluid, it's still a 2D, which is the kind we use for wakes. The advantage of this is the actual projection node. You don't need a separate node for the 3D projection of the fluid texture. So the fluid texture is its own projection in essence. So as you move this fluid, it'll move where it is with respect to the ocean. And the ocean does need to texture the displacement of the ocean. You have to use a 3D texture. You can't use a 2D texture, or it won't bump map correctly. The 3D texture for displacing the ocean is applied to wave height offset, and in this case, we've applied it's called ocean wake texture. It's actually a fluid 3D texture with the is2D flag on. So that's the setup. So this gives us something that is similar to the pond. If you create an ocean pond, but with this pond you can ray trace the reflections on it. Now to get back to the shader, let's look at some of the parameters we had to change in order to get it to reflect well. You mentioned, I said there's some, or you may remember I mentioned there's some compounding factors. One is that under specular shading, the environment normally is got a kind of a sky environment on the ocean, so that it has its own built-in environment map. If you try and ray trace reflections in addition to that environment, you will get the environment will wash out the reflections. So make the environment completely black. Also increases specularity all the way up. There is also an effect with the ocean. Let me first just, I'll step this a few frames to get a bit of a ripple, and we can actually, I can render this from this point of view. And see, we get the ray trace reflection of the yellow sphere in the water. And the reflection is stronger if we're at glancing angles, and this is sort of the way it just works with water. So if we go to a stronger, or a steeper angle, you'll see that this is a little brighter here, and that's um, the way water reflects stuff. It's more at an angle, and it's sort of determined by the refractive index. Now, you note I've increased the refractive index here in this example because a higher refractive index will make it more reflective at steep angles of view. So it'll be more reflective, say, when you're looking at it from that angle than it would be with a low refractive index. And people generally want it more reflective when they're doing ray tracing. Although, to be strictly speaking, a value more like around 1.4 or so is a bit more accurate for actually doing the way an ocean reflects. If you get into very high refractive indexes like 10 and stuff, you're starting to talk like metals and things, which are reflective pretty much equally in all directions. Now note that the refractive index does also affect it if you are doing ray trace refractions and bent rays and with the transparency, so this will have an effect on that as well as the reflections. The other thing to note is that with the ocean shader, in terms of refractions with depth, when you're ray tracing, it becomes more opaque with depth in a natural fashion. There, you don't have under ray trace options, you don't have the usual fall off parameters you have for that on other shaders because it's computed in a bit more of an integrated fashion in the ocean shader. Just one other point I'd like to make on that with the refractions is that the transparency is based on the depth to the first opaque surface. So that works okay if you've got an ocean with a bottom behind it, where the ray hits the ocean and then it goes through it and it hits whatever's underneath the ocean, and then that's the depth that the ray goes through. But if you've got like a sphere that you've assigned the ocean shader to, where it goes in one end of the ray goes in one part of the sphere and then exits out the other part, where it exits, it should use that depth, but unfortunately it doesn't. It keeps going until it hits the far clip plane or the first opaque surface, and that becomes the depth of the thing. So the transparency fall off on things like a sphere, or if you want to use it as a glass shader stuff, doesn't really work the way you want. Other parameters on the ocean shader worth noting are the trough shadowing. The trough shadowing just makes it darker inside the deeper portions in the valleys of waves a bit, as if the sunlight is being shadowed more in those deep crevices in the waves. Generally there's a fair bit of translucence on the ocean. This kind of will simulate just the way light kind of scatters around in the surface. Diffuse, if it's a fairly thick opaque ocean, there might be more diffuse, like if you had a lot of mud particles and stuff in around the surface. It behaves more like an actual surface. That's and one other interesting point is on the ocean, we do have separate glows for specular and glow intensity. So if you just wanted to make the actual highlight glow like a sparkly kind of ocean reflection, you can just use specular glow on the ocean surface. Oh, and another parameter that you probably want to cover in order to get good reflections is when you're ray tracing, you want to cast shadows onto the ocean, and you want the ocean to receive the shadows, so that when it's, let's say, backlit by the sun or something, that the actual lack of a shadow on it and the glow from the watercolor is not washing out the reflections. That's another factor that can kind of hide the reflections. Many times you'll want to fake caustics instead of doing full-blown real caustics in mental ray. So a way of doing caustics, let's say if you're just using the Maya renderer, is to use a light that you project an ocean texture down. I'll show you, there's an example in the fluid examples under, if you go, just click the tab here, we go to ocean examples, and we've got a bunch of ocean examples here that ship with Maya. I'm going to grab the underwater example, and this creates, we've got a directional light. It's a full underwater environment. It's also got fog, and I believe it uses the underwater physical fog simulation. And then the light here, if we look in the attribute editor, on the color, we've mapped an ocean texture. And this ocean texture is animated over time at a certain rate. I could just delete the expression here, and I'll show you. As we change time, you can see that that ocean texture kind of evolves and moves in a fairly realistic caustic fashion. And so what we're doing is we're just taking this texture and projecting it down the axis of this directional light. If we render the scene, there's it from kind of a distance. One of the nice things about this caustic is that it goes on forever, and it's relatively fast to render. So you can get nice details in it, and it'll project over top of any objects you have in the scene. It's a little challenging sometimes to the edges of pool and stuff, so that you don't get caustics like on the outside of the pool and things like that. You have to kind of control where your light is, and there are a lot of different kind of lights you can use to do that. You don't have to just use directional light. But let me look at some of the other things here. The actual trick in getting the caustics here on the texture is to use the wave peaking. And so we have full turbulence on the waves, and then the peaking is 1.5. You can only get that value by actually typing in here. If we click here, that we max out at 1, and you can see it's still fairly smooth with a wave peaking of 1. But if we go to like 2, say, you see you get these nice fine lines. And it actually, for shallow water, it's a fairly close approximation to what light would do as it goes through the waves and the way it would get focused. So if you combine this, say, for shallow water with the exact same ocean texture but used on the ocean part for the displacement and minus the extreme peaking, you can then get a caustic that will correlate with your ocean as well.
Here is a scene where we use the ocean shader to create an indoor pool with caustics and global illumination. So we use Mental Ray to render this. The interesting thing about this scene is that it has been optimized for using Mental Ray render global illumination. And just to keep in mind that it's something that needs to be used carefully. You can't just press a button and allow everything to be rendered with photons. So essentially what it is all about is having one light as your photon emitter and optimizing that. So if you look into the relationship editor and you select these lights, you can see that not all of them are connected to everything. And especially this is the photon emitter. It is connected to all the things that I need, but at the same time, it's not going to hit the things that I don't really need. Also in the render globals, if you take a look under caustics and global illumination, you'll see that most of the job is being done by final gather, and I'm using a little bit of caustics and global illumination. Again, the numbers over here are something that you should take a look, because if you crank up these numbers, your render is going to take much longer. Also, the ocean shader that I'm using, if you look at the ocean shader, the water surface has got this ocean shader assigned to it. You should take a look at the ocean attributes that we are using over here. And these are the common material attributes, under which refractive index, transparency, translucence, these are the attributes that actually give you the right kind of water that you're looking for. Also look at the reflections and refractions, ray tracing options. There are some Mental Ray options over here, which I'm not really using, but there are photon attributes, if you want to crank them up or tweak them, you can switch this off and then do your own customize photon attributes. So I'm just going to show you that over here, this scene was constructed the way it was constructed. There are a couple of lights over here that I used for casting light underneath the water. There are 4 other lights on the outside, and the photon emitting light is one of those. So if you look at that light, it's this light that sits in the bottom. So the idea is that the uh, light that is inside of the pool is the one that I want to use for emitting photons. And once you look at the final render of this, then you'll get an idea why I am emitting photons only from this light. So let's take a look at that. So here's a rendering, final render of this, and this file is pretty much ready to render, and you can see that there is caustics on the roof of the building, and there is caustics on the side of the pool, and it is all coming from the light that is underneath the water surface. And rest of the lights, I don't really need them to cast photons. They're just there to give you an ambience. Here's another example of similar kind, in which I created this scene where the pool was sitting outside. So I'm trying to simulate sunlight as well as the caustic. So the light is coming from the outside of the water, so above the water surface, and hitting the water, and then it hits the inside of the pool. So the photon emitter in this case is this light. So if you look at the attributes of this light, it's got it's emitting photons. It's got this yellowish sunlight type of photon color. And then I would suggest that you take a look at the render globals as well to see what exactly is going on in this scene. So I'm going to show you the final render that I got out of this. So here's the render that came from this scene, where I'm trying to simulate the sunlight creating some caustics on the side of the pool, which you can see on the rim over here. The ocean shader works just like any other shader when it comes to mental ray, just that you have to make sure that your common material attributes are the way they're supposed to be for a shiny water surface. Other than that, rest is optimizing your mental ray global illumination attributes. This is a scene where we have the light inside the pool, and just to show you how the caustics work over here, the light that you see over here is creating all these caustics on the wall of the pool. The camera is under the water surface this time.
Here's a scene, ocean spray particles. Now this one is an example of how to emit particles from where your waves peak on the ocean. So it uses the height of the ocean, and where it's higher, it emits particles. So the basic technique is that we have an ocean plane. Let me just show it here. And the ocean plane is emitting a bunch of particles, so it's a particle emitter. But now when we emit the particles, we want them to emit from the surface of the ocean. So we have some particle expressions that set that up. Now if we look at the expression in close here, here's my creation expression on the particle. we use color at point, so we get the position as a vector from the particle. We put the x and z position of that into these variables, and we call color at point with that x and z position. That gives us the height of the ocean at that value. We could also get the actual color of the ocean if we wanted at that point, but if you just ask for the alpha aspect of which is a default when you ask in color at point, then it gives you what will be the alpha output of the ocean shader, which is in fact the displacement. So we just take the this returns color at point, always returns an array. You can ask for more than one point. You can ask for a bunch of points, or you can ask for a range of points from color at point. So you can give it a min and a max bounding region on your texture or ocean shader, and say, give me a 20 by 50 grid of points, and then that's returned in this float array, and you can index all those, which is more efficient if you have to access a lot of points at once. In this case, we have one particle and we want to know 1 point. So we get its displacement, and then we check to see if this displacement, which will be the very first value in the array, is greater than the spray height. So this spray height is a dynamic attribute that we have added to the ocean plane. So if you open up the ocean plane and look under extra attributes, you'll find the dynamic attribute spray height. And you can adjust that to determine the point at which the particles will emit or not. Now, if the point is greater than the spray height, what we do is we take the height value and we set the particle y position to that height value. So here's this y we're setting to the displacement. So now we reset our particle position to its existing x and z position, but in the y, we set it to the height of the ocean. So now the particle emits as if it's emitting off the surface of the ocean. And then we give the particle also a random lifespan here. We give it a rand value and plus a little bit so that they don't just always die right away. So now that it'll have a random lifespan. Otherwise, we set the per particle lifespan to 0. So that's a way of killing the particle. When you set the lifespan to 0, it'll just die. So we actually are emitting a lot more particles than you see, and most of them, because they're below the height threshold, are simply killed at birth. Now, that's the creation expression. We also have a runtime expression. Now, the runtime expression looks somewhat similar. We get the particle position, we do a color at point, right? And that gives us the displacement value. And then we look at the difference. This y diff is the difference in the height between the particle position and the ocean surface. So if we're up higher than it, we can use that to pull us back down to it. So there's on the ocean plane, there's also another added attribute called suck force. And so as you increase that, the position will be brought more down onto the ocean. So this is why the particles, when they emit now, as the ocean goes down, they kind of tend to flow along the surface, and they will move up and down with the ocean as they travel over the ocean. One of the problems you get if you just emit them is that when a wave goes down, it pulls the air down with it. So it will suck mist and particles down as it moves down and then push it when it moves up. So by adding this additional wave suction force, it makes the simulation more realistic. And again, we can, this check here, we just say if the particle is less than this min elevation, again, it's another dynamic attribute. Min elevation we add to the ocean plane. This is the min distance that the particles can be above the ocean, so they can't go any lower than that. And because we're using multi-streak particles, we can set that min elevation to be about the width of the multi-streak so that none of the particles disappear under the ocean. You could also do things like, if you wanted like some kind of spray to die, you could say if the height of the particle goes below the ocean surface, you could then just kill it. But in this case, I'm allowing the particles to surf along the edge of the ocean. And we just set the particle position to this new corrected position at the end of it.
So the next progression from what we have seen before was we combined the ocean shader with traditional particles that Maya had. Now the next thing that is kind of similar, but instead of the particles, I'm going to actually use 3D fluid, and I'm going to make sure that the 3D fluid actually emits a fluid exactly in the same way inside close to a ocean shader. So essentially what I want it to do is emit fluid where the peaks of the waves are matching the criteria that I'm looking for. And on this, in this case, the ocean plane, as you can see in the channel box, I have added a bunch of dynamic attributes like spray intensity, whiteness factor, temperature factor, the kind of color that I want to emit, density factor, velocity factor, and there's quite a bit of a list over there. And if I just play while I'm talking, you'll notice that as the simulation goes on, the ocean is getting simulated. It has got some peaks, crests, and troughs, and wherever the crests or top of the waves are more white than certain amount, I'm getting this a mist which is being emitted by set fluid adder and inside this fluid, 3D fluid. And the way it is being done is if you look at the expression editor, you will see there's this big expression that I'm using. So here it is. What this expression does is it picks up all these values that we had in the channel box on the ocean shader, ocean plane, the dynamic attributes, and pipes them into this expression where let's take a look where we actually use them. The way we actually use these values is we go through iterate through each and every voxel of our 3D fluid, which is actually creating all this mist. And if the wave height happens to be inside or above that voxel, then we know that our voxel is supposed to emit something to represent the mist or the spray that is coming off the top of the ocean. So over here you can see that I'm getting all that information, and then finally this is the loop that actually iterates through each and every voxel. And because it's a three-dimensional fluid, this loop has got another loop inside it, and then there is another loop. So we got about 1, 2 and loops, and inside all, once we satisfy all these conditions, and that way we find out that this is actually the voxel that we want to emit, then this is where we start emitting into the fluid. So once I go through all these conditions and find out the correct voxel, I do set fluid adder density. That's where I actually emit. Then there is the velocity. Now I want to make it look like the fluid is, or rather the mist or the fluid that is being emitted is actually being blown away by air or wind. So these yellow arrows that you see are kind of indicating in which direction the fluid is moving in that particular voxel. So you can see that it's being blown away and above the water surface. And the way that is being done is, if you go back to the expression, I am setting the velocity, the initial velocity, as soon as the fluid gets emitted. And once the velocity is set, I don't touch it again, so what happens is that the solver takes control of the velocity and sort of creates its own effect of diffusion. Apart from that, you can actually use things like temperature and fuel, which are not really necessary in this case. Um, so just to see that this is actually working, if you look at the color over here, I'm actually emitting white, but I could actually change it to something like a red color. And if I start playing it, let's see what happens. You can see that it suddenly changed its color to red. So I do have control over what kind of mist I'm emitting into the above the ocean surface. And now that you can differentiate between the actual fluid, three-dimensional fluid, or the mist that is being emitted, and the surface of the ocean shader, you can clearly see that it has actually picked up patches of foamy things that are on top. So the foam that is sitting on top of the waves, right here you can see that it is emitting three-dimensional, what shall I say, 3D fluid on top of it. So it is kind of doing the same function that that our particles were doing, but instead of having a expression being executed when the particle were created or born, I'm actually iterating through each and every voxel to find out if this is actually the voxel where I want to emit. So instead of killing the particles, what I'm doing is I'm actually either emitting or not emitting into voxel. And in the next example, here's an example where what we are trying to do is we are sort of simulating waves hitting a wall where the turbulence is really high, and that's where I want to emit some particles. So the way it is being done is, as you can see, there is a wake that is being generated inside a 3D fluid. That wake actually creates waves, and the waves, as they hit this wall, cause these particles to emit from this particle emitter, which is actually a NURBS curve. So if I go back to the beginning of this animation and play it again, you can see that there are no particles being generated over here. So the way I detect the particles, the condition for giving birth to the particles over here is what would be the velocity vector of this fluid. Now, the velocity vector, as you can see, is represented by those yellow arrows. And as the size of the arrows is above certain limit, that's when I start emitting the fluid. And if I go into the expression editor, which is right here, you'll see that here's the creation expression, which actually decides when to emit particles. And this is where I get the velocity of the fluid, and that's the vector that is being represented by yellow arrows. And if the velocity happens to be above certain threshold, then I make sure that the particle survive in that place, and if not, then the particle is killed. And there is also a runtime expression which actually does set fluid at a temperature, and that's the expression that creates this white looking foam, which is pretty straightforward. And I think this is what this example is all about. Essentially finding out whether the velocity is more than certain threshold. And another thing is that if you look underneath this here, the downward arrows is where actually the particles are being generated. Also, you'll notice that as the particles go down certain level, they're being killed. So it sort of optimizes our workload. So this is a kind of a progression of the previous one, and it sort of uses the same principles.
The example raindrops on pond EXP shows a simple expression that just randomly generates drops in the pond. If you look at the expression, we just have some built-in variables here for frequency and drop size and time. Loop over for a number of drops per time step. This will get evaluated each time step, and we get like a random x and y or value, and this gives us a position, and then we just say, okay, we set the fluid adder at that position at the added density value, and so we're just adding a little density to one voxel. This is sort of okay, although if you really want to get a better expression, you'd probably write a little routine that distributes the density in maybe a Gaussian ring or distribution about a point, rather than just addressing a single voxel. You'd also maybe look at the neighbors and give them a little bit of density, because I can show it better in the next example. In the rain on ocean example, it has a similar expression, and we've added some extra attributes that let us directly set the drop size. You just click on this and it brings you up to the annotation node, and we actually put the extra attributes right on the annotation node, which is kind of convenient. So if we increase the drop size, you can see it's sort of like it's the amount of density we're adding, and we get these peaks. So again, that if you had something that did sort of a neighbor distribution, it will look better. And you might note too that the waves tend to look quite noisy, and this is a result of having, just adding the drops at single points rather than a nice smooth distribution of points. If we do that, then you'll get a lot less of this kind of chatter here. Now let's look at the expression for this. Go into the expression editor. This does a similar kind of thing where we loop on the number of drops. We get a random seed in both dimensions, and we just simply, again, set the density of the wake texture. So nice and simple. It doesn't exactly correlate with where particles hit us, but it's simpler to do than actually computing the particle collisions. And usually somebody won't even notice. The file riverboat spray is fairly simple. We basically take create a boat and a wake. We make the wake long and skinny, and you set the resolution on the fluid wake. You need to set to match the aspect of the size value you also give to the fluid, so that it keeps the pixels on the fluid square. And we've added a collision object here, and so the waves, when they go by there, will bounce off of it. And there's also foam emission from the boat. So basically we just animated, actually the boat's not animated, it's did a make motor boat on it, so there are expressions on the boat. If you want to select the boat, you can play with it under the extra attributes. It's got like rudder, and you can determine how fast it moves and shifts and how it bounces. So the boat is actually bobbing on the ocean surface there, and we've got very mild ocean waves, so they don't compete with the dynamic wake that we've created. Now, one problem you'll have with this if you're using a version before Maya 6.5 is that if you turn on wrap on the boundaries on the wake, fluid wake, so that if you wanted to get reflections off the boundaries here, right now they're open boundaries so that the waves just go off the edges, but if you wrap them, it would crash. In versions prior to 6.5, there was a problem with non-square wake indexing when you've got wrapping edges or hard edges, and so just be aware of that if you're creating wakes before version 6.5. that they had that bug. Now the spray is also another element of this. This is just a really easy cheat. You just put like a couple of emitters on the side, and you could use little volume emitters and just kind of orient them to be the direction of the surface, so they flow in the direction of the surface. And you can get fancier and have expressions that emit more when it's going down than when it's going up and stuff, to get a good spray off the front of your boat.
What I have over here is a example where you can use some of the techniques that we showed before and use them to create a boat with which sort of splashes around some foam, and we're using particle emission for that. So if I play the animation over here, you can see that it's emitting some particles that sort of hit the hull of the boat and then bounce off, fall into the ocean, and then as they fall into the ocean, they also emit some foam in it. The trick over here is positioning this curve that you see over here in such a way that the particles are created as close to the hull as possible. And you might want to put another of these emitters in the front of the boat to create some extra particles. So if I look through this view, you can see that they're bouncing off the hull. The way to control the emission is to, if you look at the some of the extra attributes that are on the ocean plane over here, you'll see that there are some extra attributes, and you can increase the amount of emission through one of these attributes. You can add extra foam by increasing this. You can change the velocity threshold at which the particles are being emitted. You could actually increase the upward velocity at which the particles get ejected by increasing that. Or else you could give them extra bounce by increasing the extra velocity. And all this is connected inside the expression editor, which is over here. And this is the emission creation expression that actually controls it. It takes in all these extra attributes and pipes them into ultimately somewhere over here. So what I'm doing here is I'm taking samples of the velocity of the ocean. If the velocity exceeds certain amount, I pipe it into the velocity of the particles that are being created. The other expressions are also pretty much similar to what we have seen before. So if I play the animation, and I'm just going to hide the attribute editor over here. So through this view, you can see that the particles are bouncing off the hull. They are a little bit too bouncy, but you can adjust that through the extra attributes that we have added. So it's kind of similar to, it's sort of based on the same principles that we have seen before, in which the boat essentially wasn't moving, it was a wall. But in this case, it's a boat that's actually moving through the water and it's creating turbulence.
The file splash demo is more of a complete example. It's designed to render showing some of the ocean ray tracing with reflections and the way depth and color change on the ocean. And it's got a fairly complex particle and expression setup, so it's worth going into. We have this little object that jumps into the water like a penguin here, and then he swims around. And as he swims, he releases bubbles under the water which float upward. Those bubbles die when they hit the surface, so they don't continue. When he breaks the surface, it automatically creates spray. That spray then goes down, and where the spray hits the water, it actually creates ripples, and it also emits foam. So we could actually look at that at the beginning, and you can just change the animation, and you can keyframe the actual motion of this guy is keyframed, and if you change the keyframes, you'll get different splashes, and all dynamically happening as secondary animations. So let's look at, say, the initial splash here. As those particles go up, they come in and drop down, and we can look at that in more detail. We've got like an ocean preview plane here, and we can you can move that around, and we could scale it, or we could increase its resolution. But if we just want to see a particular part in detail, one way is to kind of scale it, and that way we can see exactly how the stuff is locally behaving here, and it doesn't really slow down any because we're just looking at a portion of it. So there's a few things happening. We've got a wake created with foam here. So there are actually two fluid nodes overlapping, which is done through the fluid effects on the ocean. You create a wake. We've got our overall ocean. And note that the wakes blend in their effect towards the edges. That's the fluid drop-off allows you to kind of soften the edge where these waves, so waves at the edge of the wake won't suddenly have a hard cutoff where they go into the ocean. The expressions to get this mission right are somewhat complicated. Let's watch slowly as we move here. You'll notice that there's this little disk that follows the surface around. You'll see the way the disk is constructed is such that he emits particles outward from it like a splash. It's sort of curved a little bit, and we're using the surface emission off of this, so you can shape that ring to get a different kind of spread of particles. There's an expression that keeps him, he's basically, his XZ position is the same as our little character, so as he moves, we've just simply connected the XZ to this. And then the Y position is done by doing a color at point on the ocean, and to get the height of the ocean, so it'll kind of bob up and down on the surface of the ocean like a little buoy as it moves along. And then now to determine whether or not we need to splash, we track the velocity of this guy moving inward, and let me show some of the expressions. Expression 2 here. You can define on this, you can change the particle spray rate and bubbles rate. I haven't bothered creating dynamic attributes for this. They're all just right in the expression, and you can kind of set those variables, or you could create dynamic attributes for that. We find out the velocity of our little penguin guy by doing get adder frame -2, dash time frame -2. This of the translate y. And so this tells us the last y position, and then we just get nerve sphere translate y to get the current, and the difference of that tells us the y velocity of it, and so we can know if it's going up or down. And then by knowing that distance, we can change the emission rate. And it gets a little more subtle, and there's some cutoffs and speed things, but that's basically what's going on. We've got with these other particles some expressions that handle the bubbles rising, and also this is just creating the particles so that they create on the surface and die when they fall back into the surface. So you can pull out those expressions and kind of analyze them to see a bit more what's going on with this example. The shading on the ocean has also been set up for good ray trace reflections, and also to avoid chatter off in the distance on the shading, we use production quality settings with contrast sensitive, which is important if you want to get rid of chatter on the ocean near the horizon. The regular production settings aren't enough to resolve that, but the contrast sensitive settings generally help with that. Okay, I'd like to talk a bit about creating a wake, just the basics of it. With a pond, we can, the idea is first you either create an ocean or a pond, and then you create a wake. the wake is basically a fluid node that has an emission on it. So let's look at the pond example simpler. So initially we create a pond, it doesn't really do much. You have to emit into it. You could emit from an object into the pond, or you could emit from a surface. If you pick the pond and you say pond create wake, all it does is it creates a little emitter, right? And it emits some density into the pond. Now, one of the things about a density emitter that might be worth showing you here is here's the emitter here. It's a volume type, so it's got like a bound on the emission. And one of the problems is you get like, you can get kind of hard edges towards the edge of the ripple, plus it keeps emitting. That's partly because the drop-off is it doesn't go to zero by the edge of this volume. So if we increase the drop-off rate, it'll give us a smoother profile, you see. And you can see there's still a little bit of a harsh edge where it's still clipping a bit at the edge. That means that the density is really not all the way to zero at the edge of that volume. So increase the drop-off, we'll get even more. And one of the things it also does when you create the emitter in this fashion is it turns off jitter. If we turn on jitter, you can see it's kind of noisy, which is okay when you're emitting into a density value, but when you're emitting into water, the subtle variations of the jitter just create this turbulence, so you probably don't want that. So if we just start like that, we don't have any turbulence. Now, the emission also has some other nice features. Let me just scale up our emitter here a bit so we can see this a little bit better. So here I'll make our emitter a little bigger, and we'll get a big thing. Now, right now it's emitting kind of constantly upward, so it's like having a water pushing up from underneath. We could, if we want, you can make the density emission negative, so -5, and then instead of pushing upward, it'll push down. Or as a wave, you could make it oscillate. So we could type in, this is one of my favorite expressions in the attribute editors, you can type in expressions by just simply typing equal, and then whatever you want, it automatically creates an expression. So we could say the density is equal to the sine. Sine creates like a little oscillating thing about 0 of time. And then we could multiply that by 5 if we want it to go from -5 to +5. So now we have a little expression, and this goes up, and then it'll start to push down. It's kind of slow right now, so we could speed that up. I'll just edit the expression, and we could say take time, and we'll just multiply time by a value, say 10, and that'll make it oscillate. It's as if the time is 10 times faster, so it'll oscillate that much faster, right? So now we've got like a little wave oscillator there emitting the wake, and it's fairly smooth. And let's just turn this off, so I'll delete that expression, and we'll just go back to the straight emission. And note, there is a little bit of a fallback initially as it drops down, and then it goes into kind of a steady state. We have turbulence on the emitter, which is quite useful for a lot of effects. So if you look at the file Spring Burble, it basically uses this effect. So we can change the speed of the turbulence, and it's sort of a smooth noise function within this volume, and as you increase the frequency, it'll get more detailed. So if we go 5, 5, 5, you know, then you get this very fine turbulence, and it's relative to the size of the emitter. So you can do some nice kinds of emissions using that. Now, if I wanted there to be a little foam emitted as well, you need to, when you create the wake, it's at that point you specify foam, and then it will set up the fluid so it's handling foam. So when we do that, what it does is our fluid now has a temperature grid. The temperature grid is used to handle the wake stuff. So we use the notion of heat emission to handle foam because we don't yet have an actual foam emission under fluid attributes, so we kind of co-opt heat for that. So now when we emit, you can see it's white where our emitter is, and so there'll be some foam, and there's actually the reason why it's slower too is that there's some temperature diffusion on that. It actually speeds up once the wake reaches the edge. Um, but then as you move, the foam, in this case, unlike the ocean foam, this foam has memory, and you can kind of use this on fluid textures so that when you emit, the foam stays around, and then you control how the foam stays on the fluid by the dissipation. So because the foam is temperature on this fluid, if you want the foam to dissipate faster, you can go under the contents details temperature, and you can use the temperature scale diffusion and stuff. So the diffusion will determine how much it just kind of blends outward. It's sort of like a blur filter in Photoshop at each time step is the way diffusion works. If we set the diffusion to 0 now, if we have dissipation, that's the amount that it fades out over time. So you kind of couple that with how much you're emitting, and that determines how much foam there'll be on the surface. And then for shading it, the foam is on this, it's mapped into the temperature maps into the color. So where it's hotter, or where we have more foam, the color goes more towards this white color. And then under texturing, if we wanted, we could texture the color, and if we wanted to texture that sense of foam to give it a little detail, we could increase the frequency on the texture, and if you use inflection, you can kind of create things that are sort of ring-like with the foam. Maybe inverting the texture with inflection might be a little better. So you can get some nice effects, and then you can animate the texture time so that it varies. Actually, a good one to animate, if you animate the texture time, use the space-time noise, because it'll kind of bubble in place as texture time is animated, and it won't kind of drift to one side or the other. Now, foam is a little bit different, and foam and wakes are a little bit different on the ocean than on the pond. They're actually more complex on the ocean. So let's just create an ocean. Now, so here's our ocean with a preview plane, and we'll go ahead and ocean, create wake, and I'll include foam. So if your foam creation is not 0, it'll also create a second emitter. So now we've created the wakes. So now we not only have an emitter, but we have added a fluid. In fact, we've added 2 fluids. So if I scale that one down, you can see we actually have 2 fluids that are overlapping. One is a wake fluid and one is a foam fluid. And this gives us, by using 2 fluids, it gives us a little more flexibility. The wake, lets us define the bumps, but then the foam lets us use any kind of diffusion model we want, to handle the foam aspect of it. Now, these are both now textures on the ocean shader, so they're not just aspects of the fluid the way they are with the pond. One thing to keep in mind, the difference with the pond is actually just a fluid node itself. It's a fluid shape. In the case of the ocean, it's a bit more of a complex setup. We have a surface with a displacement map, and we've got an ocean shader, and then the wakes are added as textures on the ocean. So the wake texture on the ocean is applied as it's mapped under the wave height offset. So the wave height offset's now controlled by the wake, which adds an additional offset value on top of the ocean. And then the foam is the foam offset is what it's mapped into. Now as we run the simulation, you'll see we get this added wake on top of our ocean waves. Now if we want, we can only see, if you only want to see the wake effect on the ocean itself, and you don't care about the textural sorts of ocean waves, just make the num frequency 0 on your ocean, and it will also, it'll generally be quite a bit faster. And you can preview the wake that way. Now, if we have this is a boat, say, we could if you had a boat selected when you did create wake, it would automatically kind of size this wake emitter and fit it to your boat so that it would then move with your boat. But we could just do a couple of keyframes here. So I could go down frame 1, I could set a key there, and then we can translate this thing, a bit, and set another key. And it's probably moving pretty slowly, but you get an idea. So as it moves, and let's have a little bit more detail on the preview plane so we can better see what's happening here. So lots of little fine ripples. Now you notice that we're getting a lot of chatter and noise on those ripples. Let's go in and we can make that wake a little smoother. So I'll select the emitter, and let's just delete static channels here so we only have our animated bits. Okay, now the drop off I'll increase, which will make it a little bit smoother on the emission. There we go. And then notice the ripples are actually fast. So if this were like an ocean liner, right, these waves would be moving too fast. And one of the problems when you create wakes, unfortunately by default, the speed of the waves on the actual ocean, if you're showing the ocean waves, is slower relative to the speed on the wake. And it kind of depends on how big the wake is and stuff, how fast the waves are going to be moving. What you want to do generally, because they tend to be too fast for like the scale of the ocean, select the wake texture, and this is the same on the pond as well. If you want to slow down the wakes so that they don't move outward as fast, if you want to get a nice V-shaped wake, say, and then under simulation, it's simulation rate scale. So we'll just make it say 0.1, and now the waves will move at 1/10 of the speed that they were moving at. So now at this kind of slow rate of travel, we'll get sort of a V-shaped wake. Even that, the waves are moving relatively fast. We could even lower that further, so we get like a real sharp V shape on the wake as our object moves. And then it's a matter with the foam. You can, if you want the foam to last longer on it, you can go to the foam texture and adjust the. It's the same thing. It's the foam texture is using. It doesn't have a density grid, but it does have a temperature grid. So we're keeping with the convention of emitting into temperature for emission of foam, and then if we have the dissipation less on the foam, and we could turn the diffusion down too if we wanted, then the foam will just sort of be emitted and it will stick around longer. It's still dissipating fairly fast, so I'll turn the dissipation all the way down. Notice the foam is also moving outward. This is because there is a turbulence on it, and at this rate of speed that turbulence is kind of high, so I'm going to lower the turbulence speed and the turbulence strength, because it's just a purely almost a textural effect on the velocity with the turbulence. It just kind of pushes the foam around with this turbulence. We can again lower it, and you can set the frequency based on the scale if you're seeing, and generally you control it and get good turbulence that way on the fluid. So that's the basics of the way that the emitters work. And again, once again, you can pick an object and you can emit into the fluids as well, so you're not limited to just emitting from these standard emitters into these wakes once you've set up the wakes. Here's the file boat. Now this one is primarily an example. It's not fully rendering, and we don't have the dynamics and stuff in the boat, but what it does show is use of creating an ocean wake and then emitting into it from particles, and there's some expressions going on. There's also, you can see attached to the paddle, there is an emitter, so that emitter emits density into the fluid and emits wake into the fluid. And as well, there are particles emitted, and when the particles hit the surface, they have expressions that transfer a little density into the foam, and I think also the wake grid. So you can pull that apart and see how those expression works, those particle expressions. And it's actually quite similar to the Splash demo file as well in the way that some of that stuff works. Here's the file, Big Boat Anim. This one is a full boat with wake simulation, and it uses paint effects for the spray on the wake, although you could modify it in a similar fashion to use particles. So it has a full ocean. The rendering set so the ocean renders fairly well. So if you want like a ocean rendering reference, this one might be good. And also the spray renders, and the spray renders fairly quickly. It's paint effects using thin line and the multi-streaking in the paint effects, which is fairly fast for rendering a lot of spray. It showed in simplified form in Hardware Draw here, but check out the renders to get an idea of what it looks like. Now, the trick here is partly to get the spray to emit from the edge where the ocean hits the boat, right? So we need to know what is that colliding region of the ocean with the boat hull. So in this case, the boat hull is a NURBS surface, and there is an additional NURBS plane created here, and we have its shaded display. Actually, its full rendering is turned off. We don't render this plane at all. It's strictly a reference NURBS created to do the intersect. Now, to position the CVs on this NURBS plane here so that they're offset, there's expressions that set the CVs using color at point. And we have included a MEL script that lets you set one of these up. It's called Ocean NURBS Preview Plane .mel. So if you put that in your scripts directory, you can type in Ocean NURBS Preview Plane, and you check out. I'm not sure if there are any arguments or if it just creates one for the current ocean. But I think there are some arguments. You give it the number of CVs you want, right? So you can have a denser, grid. Generally, you want to keep it as non-dense as possible, because it is somewhat slow computing the offsets if you've got hundreds and hundreds of CVs that you're doing inside the expression. But it does position the CV offsets, and then once you have that, you just simply do an intersect of this with the hull, and you get in this case I've got two sides, so I get two curves because I've done the intersects on either side. Now these intersects, these intersect curves, then I make. In this case, it's not good enough just to have a curve on this plane. What I want is a curve that's right on the hull, so I know what the angle of the hull is. So I turn that intersect curve into a curve. I project it onto the hull, so I now have a curve on surface on the hull. And then from that curve on surface, you can do you can select like a spray brush, or you can actually take this brush if you want. You can save that as a spray brush, and you attach paint effects. You can do curve utilities, attach brush to curves. So you get like some kind of a spray brush, and you attach it, and then it creates a stroke that then follows that changing curve. So now we've got this paint effect stroke, and this paint effect strokes, if you look on the settings, the spray brushes, here's one. It started with the sprinkle thing. We use a thin line, which is fairly fast to render lines. And then under tubes, it creates tubes, and we have some flow animation. So that determines, the flow animation determines how fast the gaps kind of move down the line. So if we slow that down, or we could even reverse it, we could have the gaps moving inwards. So now the spray is kind of hard to see in this because it doesn't display as well in Hardware Draw. But the gaps are now moving inwards towards the center of the boat, right? As it moves. So you can play with that to get the flow rate the way you want and stuff. There's some added. You can set the gap spacing. So if you want, a lot of space between the gaps, and the gap size could be smaller, so you just have individual particles, or you could have big streaming things coming off of it. Kind of depends what kind of effect you're after on that. And the actual angle here, now you notice how the angle, there's more, it's longer here and the angle's more vertical, and then as it goes to the back, what I've done is on the actual stroke, we've got pressure values, and the pressure is mapped to tube length, tubes per step, elevation. We have under the pressure settings here, you can actually hand edit these pressure values if you want. So I could set it 0, 0. It might not show up too well unless we play back a little bit. Yeah. Let's see. There's a lot of pressure settings to set. I think, is that the front? Okay, there's this other side. That's why I'm not seeing it. So here you can see the effect over on the other side, because we have 2 of these strokes, right? So by setting the pressure values along the stroke, you can set where it's strongest and where you get the most spray. So I've tried to do it so there's more spray at the front here, right? If we made that like 5, then we'd get an enormous amount of spray sticking out on the front of that, right? It also affects the angle, so the angle's being pushed over maybe too much. So you can kind of control the way the pressure values map into elevation and stuff on the thing. So that gives you maybe more control than you'd get with particles. But another thing you could do is just take that curve and use it for particle emissions down the stroke. Notice there's a couple of other features with this in terms of the wakes. There are a couple of emitters back here and a wake emitter here to emit wakes and foam, so we get nice little streaming things off the back, sort of like the bow wake. So you can kind of more finely model the wakes associated with the object. And one other feature of this is that as the boat moves, you'll note that this NURBS plane moves with the boat. So what we do is we just simply take the translation of the boat, but not its rotation, and we attach that to the translation of this plane, so that the plane is always in a position where it will intersect with the boat and give us those curves, even as it turns. Here's a render of the Big Boat Anim file, and you can see we have a wake at the back with some turbulence in the foam, and also we've got the spray happening along the front edge of the boat. One problem with using paint effects for this spray is that you will get, as it moves up and down in this region, you know, if you get in close, the individual particles seem to be moving along a trajectory, but the whole trajectory they're moving along will move up and down as the waves move up and down, as that curve moves up and down, and that's somewhat unnatural because there should be a lag. When it goes up at the beginning of the spray, it shouldn't also affect the end of the spray, which is what happens because of the way the paint effects is actually non-dynamical that way. It's really more like a cycling sort of effect. So if you replace that instead with some kind of particle emission, you could probably get a pretty, you know, natural result there in the front. Although the nice thing about the paint effects is that you can get a lot of detail and particles there without requiring, it'll render quite fast. Here's a single frame more from the front. You can kind of see the spray a little better in the front and some of the detail you get in it. I've got another one that shows more from the back, and you can see the wake structure and the shading on the foam. The file painted static wake is sort of an interesting technique you can use. It allows you to paint the exact shape of a wake, and on the fluid there's no dynamics or anything. All it is like a texture really that you can paint into, but then you have the nice thing that you can kind of see the wake and you can transform it. So let's say here's our object, and we have sort of an ocean, and it's got some observer speed on it, so it's like the ocean is moving. That's also good for rivers and things. And we have this object, and we're just imagining it's moving forward, even though it's actually stationary here. Now, if I paint out like this, we're kind of defining a bump for wake, and you notice it even affects our object, and our object will bump up over that. And you could, you could try and define what you think is about the right wake with fall off on the edges. And we're sort of also displaying our texture while we're in this mode. The moment we go out of the paint tool, we're painting density on the wake grid that's in here. Now there's also an initial state file on that. So if you, we bring up the attribute editor here. The initial state, this texture here, if it should find it on disk. So when you first run this, you should see some kind of a wake there. If you don't, it's probably just because you haven't got that. It's not able to find this file with the way you've got things set up. So this is obviously an extreme example, but you can also you can paint the foam. So if we go back, I've selected the foam grid, and we can, or hang on, no, I didn't select the foam grid. I've selected the wake. Let's go back. I'll select the foam. This is our foam grid here. And now I'll paint that. Now to paint into the foam, we'll add contents, we do the paint fluids tool, and the options will set it to paint temperature now for the foam thing, and we'll just add into the values. And I mean, this is not very good, but you could do a real nice foam painting that looked about right. And there's even texture on this thing, so it'll add an animated texture to the foam you paint. So now we'll go back and look at it. So now we have the object, and it's emitting this enormous wake in the foam. Now we could pick our objects, and if we go and move them, we can actually move the wake through the water and follow our object, right? So that's a way without relying on any fancy stuff, just to get the exact shape of wake and have it move along with your character. So now we'd like to cover some pouring fluid effects. Now keep in mind, even though we call them fluid nodes in Maya, currently they don't really handle two fluid simulation so well. And the other thing to keep in mind is that the fluid node in Maya is actually like a box filled with water. It's all incompressible, so you push down in one place and then it's got to go up in another place, and you end up getting these kind of goopy, swirly flows when you're trying to create a water simulation. But there's still methods you can use to achieve this kind of effect in Maya, including use of particles, which we'll get into. One of the confusions about Maya fluids is that people automatically expect that it handles the case of pouring liquids, which I guess since we call it fluids, you think would be a no-brainer. But pouring fluids are really not handled very well by the fluids node. They're really, the fluid box is modeling an incompressible fluid, so it's like a tank of water that you then put dye and stuff into, and you can make the dye look like stuff that you want to you can sort of fake pouring a little bit with it, but it's not really the best thing currently for pouring, although at some point we hope to have something that's a better solution for that kind of thing. For now, probably the best thing is third-party solutions. They're lots of packages like RealFlow, which uses particle-based technique, and some other similar packages that you can look at for that. There is, though, kind of a cheat that you can use with Maya particles, and GlopPour sort of shows a particle-based method of doing kind of a pouring fluid. So although particles themselves don't have the ability to handle self-collisions, and there are some scripts you can get or some plugins which will handle particle collisions that are available on the web, but you don't need those to do kind of a rudimentary sort of particle collisions. You can do it with forces, which is what I've done here. So these particles are generated, and they're sort of pushing against each other with a force, and they fill this up and they collide with the container and then fall out. Now, one of the problems you can see with this scene is that my particles, the width is not being respected on the collisions, which is just the way particle collisions work right now. They collide at the center point. So you can deal with this by simply creating a collision object that is hidden, that is inset by the particle width from the edge of this. So in this case, we could create a bowl that's like inset, again by our particle width, and the same for this. You'd have an inner cylinder that would be your actual collision cylinder. But it's not set up that way in this example. Now, in terms of rendering this, we use a blobby particle render. So if you select the blobby particle types, and it's not a terribly sophisticated render in this, but if we look in the render view, you can kind of see the result you get with rendering. It's gloppy, and you can make it transparent. And to make it look better, you can ray trace it and get refractions with the ray tracing and stuff. And you can actually get pretty good looking water if you play around with it using this method. It tends to be a bit goopy and blobby and serial, or you can see the fact that there are balls inside it when it animates, but it's not too bad. Now, to set it up, the basic workflow is you create an emitter, emit some particles, and then